Good evening, everybody. Welcome to day 3 of ATAL-FDP program on AI and emerging technologies for sustainable energy and climate adaptation at IIIT Kottayam. So today's speaker is Professor Tiju Thomas. Professor Tiju Thomas is an interdisciplinary faculty and professor with the Department of Metallurgical and Materials Engineering, Indian Institute of Technology, Madras. Professor Tiju holds MS and PhD degrees from Cornell University, New York, USA, and works in interdisciplinary areas that straddle materials engineering and allied areas, nanochemistry, electrical engineering, applied physics, and solid-state chemistry. Professor Tiju also has an MS engineering degree from the Theoretical Sciences Unit from Jawaharlal Nehru Center for Advanced and Scientific Research. He heads the Applied Nanostructures Engineering and Nanochemistry Research Group at IIT Madras, which focuses on developing compositionally complex oxides, oxynitrides and nitrides, and nanometals for achieving engineering ends. Professor Tiju Thomas was awarded the Inspire Faculty Award by the DST, Government of India, in February 2012 and Fast Track Young Scientist Award by DST in May 2016. Sir is also a member of International Center for Clean Water governing body. Problems concerning the functional properties of materials are of abiding interest to Professor Tiju, in particular the next generation energy storage, supercapacitors, hybrid energy storage systems, nanotech-enabled solar energy harvesting and solar-driven water treatment have been the group's recent focus. The group's work on on-demand hydrogen production is internationally well known. Recently, Sir's group was in news for developing technology to make supercapacitors from paddy waste. They were also in news for portable turnkey device to detect heavy metals in soil and water. Dr. Tiju Thomas lectures and videos are available on YouTube and they are very interesting and engaging. We welcome you, sir.
Dr. Della, greetings to you, greetings to Dr. Ravi and one and all here, all the colleagues here, all friends. So many thanks, Dr. Della, for making this possible, for having me over. That's a very kind introduction also. I want to keep it as informal as possible. So there will be 3 occasions for interaction. So the first thing is, if all of you could just populate your area of research in the chat box, just taking a minute or two, not more than that, that would be very helpful for me because I'll try to make connections wherever possible. Of course, I won't be able to make connections equally for all of you, but at the very least, I'll attempt to be cognizant of the audience because as of now, I do not really have an understanding of the audience. So if all of you could just populate a few keywords associated with your research area, that would be very, very wonderful. And in between, in the event you have, could I request all of you to mute? If you're not speaking, kindly mute, okay? You could use the chat box. Yeah. So the first thing is please populate a few keywords in the chat box associated with your area of research interest. Number 2, whenever as I talk, as we go through this lecture, it's a long lecture, so it's very easy to miss the points and so on. But if there is a certain question that connects your area of research to what I am going to talk about here or what you encounter here, do not hesitate, just populate the chat box then and there because I'll revisit these questions that you spontaneously got. Okay. And I will revisit these questions as much as possible, which you have spontaneous. All of you will have to mute. Dr. Ravi, could you mute everyone so that
Yes, sir.
Yeah.
Sure, sir. Sure.
So all of you kindly So all of you, when the lecture is on, at that time, you may have spontaneous questions. Populate the chat box with those spontaneous questions. No question is silly or any such thing. So just populate. because I'll use this to sort of foster some conversations at the end of the discussion. And at the end, of course, we'll have open discussion. So three occasions for interaction. The first one is right away. Over the next 1 or 2 minutes, if you could populate some keywords associated with your research, I would be very grateful. And be prepared to populate the chat box spontaneously over the next 1.5 hours. Okay. So I will maintain silence for a minute when you populate the chat box. Please populate. So Dr. Ravi and Dr. Della, you could break the ice by starting the population. You could
Sir, I
populate
have.
just a few keywords associated with your area of research.
Yes, sir. I have also shared here.
Populated. Okay. In chat box. How do I explicitly look at the chat box entries only and no other entries? Because I don't want to see the traffic of people coming in. I just need to see the entries coming in. So what should I be doing?
Sir, usually we just have to take the chat. So we'll be able.
Yeah,
Sir,
chat is
IT
what I have
support.
chosen. Okay.
IT support, can you please reply?
Sir, in right side,
I don't need to see the.
sir, in bottom right side, chart is there. You click on that. In that, continuously you will get the new ones. You can check, sir.
Sir, I think it is also showing the
It shows
admit
that
also.
mute
Because that is what is
video.
that's overriding everything else.
Okay.
That's the problem. Okay, okay. All right. So now I see some messages.
Sir, I think you can pop out the chat window, right? Some option it is showing. Even you can pop out the chat window, sir. That option is also there.
You can do the control H.
And there is a pop out icon also. And maybe you can maximize if you just want to read the chat.
Yeah. Oh, AI. Oh, wonderful. Very good. Now I'm able to see some entries. Some people from electronics doing sustainable energy, education, construction. Some people say very interesting.
Image
Human resource
processing, natural
development,
language
natural
processing.
image processing, data science. Very good. Okay. All right. Okay. So I get a sense now. So I must say that, like many of you, I began as an electronics engineer, and then ended up becoming very interested in materials for electrical engineering, electronics engineering, and so on. And that's the context in which a lot of my work took shape. And in recent times, I have found that that knowledge has been very helpful even in contributing to cutting edge areas in water treatment, electrochemical energy storage, and so on. So you will get a sense of it. Okay. So most of my work is on energy water nexus. By energy water nexus, what we mean is, can we be very cognizant of the way in which we are using energy and ideally rely primarily on renewable energy, have a life cycle, a cradle to grave assessment of materials and devices when we think about solutions for water? And can we also think about clean hydrogen? Okay, going beyond what is today black hydrogen, which is primarily the hydrogen that is used in our laboratories, energy storage, materials design. Okay, so these are what I primarily work on, and many of you come from electrical, electronics, computer engineering backgrounds, and you can connect to things that I'm going to talk about. There's a lot of science also in what I'm going to talk about. So I'll try to make it as accessible as possible and stress key points which I think will be very useful for your research, given some sense that I have gotten of the composition of this particular audience. So we'll talk about computational design to system implementation in the context of nanomaterials that are used for water treatment and for electrochemical energy storage. So I am from IIT Madras. I am formally affiliated with the Department of Metallurgical and Materials Engineering. Although, as I said, like many of you, I am an electronics engineer, I am an electrical engineer, and I also primarily use a lot of materials design principles in order to solve problems associated with energy, water, and so on. So my campus, this is a representative picture. Dr. Della did her PhD in IIT Madras, and she can attest to this. Something like this is actually a common scene in our campus, and you're most welcome to come down. I'll be delighted to host you or to facilitate your research in ways possible. Okay, and my WhatsApp number is given here, and my email IDs are also given. In fact, instead of this @iitm.ac.in, you can also send it to @smail.iitm.ac.in. It is connected to an app, and I tend to respond very quickly that way. So most of my research is connected to sustainable development goals, and many of you are faculty, I am told, so you are already aware of sustainable development goals. For your departmental vision, mission, and so on, you would have written sustainable development goals and allied activities. So the sustainable development goals that I primarily focus on are SDG 6 and 7, that is clean water and sanitation, and affordable and clean energy. And in fact, the two of them are not separated, they are together. They become very important when considered together. And indirectly, of course, it is connected to the kind of things that all of us are interested in: decent work, economic growth, industry, innovation, and hence fostering further infrastructure growth, and so on and so on. And of course, it also connects to sustainable cities, communities, because the techniques and the technologies that we'll talk about here that were developed connect to using renewable energy and storing them appropriately, or using them for water treatment purposes. So it connects to even responsible consumption and so on. So many SDG intersections will be seen in this particular talk. I'm very interested in accelerated materials innovations. Many of you who have colleagues, collaborators across the world, you would actually recognize that one of the things that distinguishes the developed countries from countries that are still developing as far as manufacturing capabilities are concerned is the focus on materials. So it turns out that countries that have been very successful in industry and infrastructure development are those that focused on materials and the intersection between materials and various engineering disciplines, various science disciplines. So this is, as a consequence, a central goal of my work, which is trying to accelerate materials innovation so that we can drive growth for our own society, for our society, and as a spillover, it could actually benefit the whole world. And I extensively use computation experiment synergy. This is a synergy that people from Triple IT, for example, can appreciate, because many of you are very good in computation, you like computational research and so on. And one of the things that I have tried to do is to sort of bring these worlds that are otherwise very different and disparate together. And I'll try to give examples from my own work in this particular lecture. So what are sustainable development goals? I have already spoken to you about it. And in this particular context, there have been many people who did PhD in our group who ended up contributing to these sustainable development goals. Some of these technologies are actually being considered seriously for implementation in our country. So research-wise, it turns out that most of the effort that is ongoing today is in hybrid energy storage systems. By hybrid energy storage systems, I mean systems that are beyond battery. Okay, so most of the energy storage, electrochemical energy storage, electrical energy storage today is primarily in the form of battery. I want to go beyond batteries. I want to enable hybrid energy storage systems so that we can preserve the life of batteries, because batteries do very well when there is a steady requirement of energy. But on the other hand, where there are fluctuating demands, battery life goes down, and we have been trying to pursue solutions for those kind of problems in our laboratory. Likewise, it's possible for us to use the next generation nanomaterials, including quantum dots, for energy and water technologies. It is possible for us to use concentrated sunlight, and concentrated sunlight is very undertapped in our country. It's an area wherein there's a lot of potential for innovation, but also for entrepreneurship and as a consequence, I try to sort of foster that as much as is possible. And it is important for us to also enhance the viability of hydrogen and hydrogen carriers, because hydrogen as a gas is extremely dangerous and very difficult to transport. If it is taken through pipelines, it leaks very easily, and it also cracks the pipelines very easily. So we have been looking at, in recent times, alternate ways by which hydrogen can be carried. I won't talk about all of this contributions. I'll primarily focus on hybrid energy storage systems and on solar energy harvesting for the purpose of water treatment as two case studies where computation has accelerated materials development and computation has helped the technology development in a very short time span. And that is the power of the synergy between computation and experiment. And we have to harness it in our country much more. And I do this in the context of SDG 17, which I like very much, and which is where I would like to extend a handshake with each one of you here. Because SDG 17 is about global partnerships for sustainability. It is impossible for us to make SDGs possible, sustainable development goals possible, or to usher in an era of sustainability single-handedly. I firmly believe in it, and as a consequence, most of my work has been collaborative and interdisciplinary, and I foster that as much as is possible, appreciate it as much as is possible, and I, as I said, would be very happy to facilitate it with all the people in the audience here today. And most of our work, because we are academics, are basically connect between TRL 1 to 5 typically, and there are people whom we connect with who take our work from TRL 4 or 5 upwards. Okay. The first question I would like to sort of ask as a thought-provoking question, and usually in a science audience I ask this question. Here I will actually just give an answer to this question also. So it turns out that there are properties of materials that many of you have not studied in your undergraduate. So in the undergraduate materials courses, typically engineers study strength of materials, so which is the mechanical side. And of course, those of you who are electronics and electrical engineers, you are taught semiconducting properties of silicon and taught to understand device physics and so on. So the latter category of properties are called functional properties. They are properties that are not to do with mechanical behavior, but to do with electronic behavior, electrochemical behavior, chemical behavior, and so on and so on. Okay, so I'll give you two examples. This is an example of a one atom thick connection. So just like you have copper interconnects in an IC chip, you can have essentially atomistic wires, and these atomistic wires can actually be used potentially for miniaturization of electronics. And these are the kind of directions in which people are actually taking materials. And at the intersection of materials and electrical engineering, intersection of materials and mechanical engineering, mechatronics, and so on, there are a lot of exciting problems. Likewise, this is an example wherein you have two materials, two different piezoelectric materials. Piezoelectric materials are materials that, when deformed, give rise to potential gradients. That means you can get a potential difference across this particular material. For example, if I bend this particular bilayer, what would happen is I might get a positive charge on top and a negative charge at the bottom, and hence a potential basically develops. This kind of technologies are used even in blind sticks, for example, okay, wherein a person who is BVI, blind and visually impaired, could walk around, tap on surfaces, get a sense of what the surface is, and so on. So increasingly, the dimensionality of materials is reducing, and the big question is, can we use this development in materials, in electronic materials, in electrical engineering materials, and so on, to good effect, especially as it connects to SDGs. So I will very briefly explain this. This is a slightly physics-oriented slide, but basically what this slide wants you to take home is the following, or what I want you to take home from this particular slide is that if you have a material and if you have the structure of the material and you know how many electrons are associated with the atoms that go into the material. For example, you could say it is a crystalline material, and this crystalline material has this unit cell, and this unit cell has certain atoms. And if you know just that much information, in principle, we can apply theory. We can also use now increasingly machine learning, and and then start doing innovative work in materials. Okay, so it is possible for us to do that, and I will give you examples for this. I'm, of course, because this is a broad audience, simplifying the entire story. But if there is target questions that sort of come out of a consequence of this picking of curiosity, I'll be very happy to respond to those. So some thoughts, and it turns out that internationally, okay, and this is yet to be the case in our country, but internationally, if you look at the composition of universities and also the composition of industries, you will find that material science and engineering is considered to be is considered a melting pot. Okay, all kinds of engineers, all kinds of sciences come into it. Okay, and as a consequence, every engineering discipline and every science discipline has some materials connected to it. For example, in electrical engineering, copper interconnects are required, so copper is there. Semiconductors are needed, so silicon is there. Photodiodes are required, so gallium nitride, gallium arsenide is there. Solar cells are needed, so you can actually have different varieties of silicon, or you can have the next generation of compound semiconductor, and so on and so on. So it is one of the most interdisciplinary areas of study, and as a consequence has connection to every engineering, every science that is possible. And a question that I actually posit to the audience usually is, in the case of mechanical engineering and circuit theory and so on, we have reached a very high level of sophistication associated with theory. That means you can tell precisely what the components of a circuit are, or you can tell precisely what the various mechanical components are associated with the system and predict its behavior. Is it possible for us to do that with materials? And over the course of the last, let us say, 15 years, I'm increasingly collecting evidence that we are getting to that point. It was not the case when I started my education in materials, but it is increasingly getting to that level of maturity. It is good news for all engineers and scientists. That means you can all actually contribute to this. Okay, so some examples from materials prediction to system implementation, from theory to practice. Okay, so I hope it is clear. So theory is this: it's a philosopher who is studying. Practice is a tool maker, is somebody who uses tools. So these worlds are coming together in this space. So the first example is the example of a material, aluminum ferrite. Why is it connected to SDG? It is connected to SDG because aluminum is the most earth abundant metal, one of the most earth abundant metals. Iron also, all of you know, is very, very earth abundant. Oxygen is everywhere. So if I can use aluminum ferrite, which otherwise is not used, for, let us say, light harvesting, making the next generation solar cells, or for tapping the energy in sunlight in order to purify water, that would be exciting. And in our group, we demonstrated, so Dr. Sudha Priyanka et al., she demonstrated when she was with us that aluminum ferrite, when doped with indium, can actually have a band gap of 1.12 eV, and this is direct band. Those of you who teach electrical engineering materials, electronic materials, device physics, etc., know that this 1.12 eV is very special, because it is the band gap associated with silicon, but silicon is an indirect band gap semiconductor. So it does not absorb sunlight as efficiently as, let's say, a direct band gap semiconductor material. However, the problem with direct band gap semiconductor materials is that these materials tend to very often have very wide band gap. But look at this. Here, we are predicting that it is possible for us to actually reduce the band gap to the point wherein we are able to actually potentially get something like silicon, but better than silicon, because especially for solar energy harvesting, because it has a direct band gap. Okay. Now, in addition to that, unsurprisingly, because it has iron in it, it is also very magnetic. So what Dr. Sudha Priyanka showed is, if you plot energy of a single unit cell of aluminum ferrite as a function of volume, the energy minimization happens when you have magnetization in this particular material. What does that mean? Nature likes to minimize energy. That means aluminum ferrite is naturally magnetic. This gave rise to an interesting idea. See, it turns out that making single devices, etc., can be very challenging, because you have to grow thin films and so on. Dr. Della studied with Dr. Vasa in our campus in IIT Madras. So she's aware of thin film growth. It is not trivial. It is actually a very non-trivial process. But is it possible for us to check the value that we have generated here? So another thing is aluminum ferrite is very non-toxic, very stable. So it is made up of earth-abundant constituents, non-toxic, and it has a band gap that is very attractive from the point of view of light harvesting, and it is almost like silicon, better in fact because of its direct band gap. Okay, of course, this was a prediction that was made a few years ago, and then it was experimentally validated. This is something like 4 years of work that is put together in the form of a few slides. Okay, so this aluminum ferrite was made single phase, and the single phase aluminum ferrite, that means there's nothing else, or whatever else is there is actually minimally present. Okay, was made by Bhuvana Sundari, who will be defending her PhD tomorrow. Okay, so she took the work of Dr. Sudha Priyanka forward, and she demonstrated that single phase aluminum ferrite formation is indeed possible. It is possible in a manner that is industrially viable. So we were able to use our own furnaces and so on, things that are there in almost every industry, manufacturing industry, in order to actually get this particular material. Subsequently, we found that the direct band gap is not 1.12 or 1.2 as was predicted. It's a little higher. It is 2 eV, but it's still better than many other compound semiconductors. And it is only weakly magnetic, but its magnetism is sufficient for us to pull it out of water if need be. That means if I disperse aluminum ferrite particles in water, let us say dirty water, and I want to pull it out, I can pull it out. Why would I want to disperse it in dirty water? The reason why I would like to disperse it in dirty water is because it's a semiconductor. It can absorb energy from sunlight, generate electrons and holes. Those electrons and holes can participate in reactions to purify water. And after the water purification is done, I can pull these materials out of water, which is what was done. So here, aluminum ferrite was put into dirty water, and this dirty water has textile dyes. Okay, these are the textile dyes that are widely seen in Kanchipuram, for example, not very far from here, where textile industries are there. And it turns out that over something like 1.5 hours, we were able to get rid of these textile dyes, starting with this aluminum ferrite. And then each time we actually purify water, we pull aluminum ferrite back and then reconstitute it when the next batch of water is there. And batch after batch, when the degradation efficiency of aluminum ferrite is tested, we don't lose much. Over 5 cycles, we lose only 5%. And even this 5% loss is actually because of the difficulty in pulling all of it back through magnetism. So in principle, we can use a stronger magnetic field and reduce this degradation efficiency. So once again, I would like to remind all of you, if you have questions that are spontaneously coming to your mind that could connect whatever story I'm telling to your area of research, populate it in the chat box. Okay, I will use it in one form or the other. We will use it in one form or the other. Subsequently, we tested the biological viability of aluminum ferrite. And it turns out that this biological viability was tested by using these cells, fibroblast cells. And it turns out that the fibroblast cells do not know that aluminum ferrite is around. That means it's perfectly stable, very non-toxic, environmentally safe, made up of earth-abundant constituents. It has the capacity to harvest sunlight. It has the capacity to purify water. It has the capacity to be pulled out magnetically. The next story that I want to tell you is on mercury contamination. And mercury contamination is a problem again in Tamil Nadu, especially in places where formerly there were mercury thermometer production going on. And you know, many of you might know this, that once upon a time, Tamil Nadu was the biggest supplier. I live in Tamil Nadu, which is why this problem sort of became interesting to me because I work in IIT Madras. So it turns out that mercury is there in water associated with industrial sites where mercury thermometers were being produced. And it is not surprising. And then the question that I asked myself was, is it possible for us to sense it? And in principle, not just stop at sensing, but at that point, get at all of the mercury and convert it into something that is useful, maybe hydrogen. So the connection to energy. So connecting dirty water to energy. Okay, another way of asking this is, once I get dirty water, mercury contaminated water, can I sense it? Can I purify it? In the process of purification, can I generate hydrogen? That is the question. So it's a slightly ambitious goal, but it is possible. Okay, so for this I had to learn a little bit with with a chemist colleague, Professor Edamana Prasad in chemistry department, and he used to develop molecules that were fluorescent. And we started working on this problem together, and Dr. Abdul Malik, who now continues this work on hydrogen and green hydrogen and so on, is the one who stumbled upon this result or developed this molecule. So it turns out that here is a molecule. This molecule is capable of being, so it turns out that it is not fluorescent when mercury is not present. But when mercury is present, it becomes fluorescent. That means under sunlight, under light, that water that is dirty will start glowing. Okay, and the logic behind it, the chemistry behind it is simple, but because of this audience, I'm not going to describe it. And not only that, after this process, you can actually get the mercury completely out, and in the process make hydrogen. Okay, so it turns out that you can start with this dirty water, you can check for the presence of mercury ion, and then you can actually produce hydrogen. And this particular molecule is also biocompatible. This was also done uh, with our biotech colleague, Professor Mukesh Doble, who helped us with the biotoxicity studies. And further, we try to understand the mechanism behind why hydrogen is produced. And it turns out that when you pull this mercury out, mercury, which is now in the form of an alloy, it has a lot of surface potential gradient. Okay, surface potential. So it is an electrochemical potential gradient, actually, more specifically. So because many of you are electronics engineers, let me explain it as follows. So if I have mercury alloy that I have gathered out of water, okay, then what would happen is that I can use an electrical probe, and this electrical probe is very small. It's only a few micrometers in cross section, and I could touch different points of this alloy, and I would actually find surface potentials that are very different. So that is like saying that you have many micro batteries that are sitting on the surface. Okay, that means in the presence of water, all of these battery reactions happen, and many of these reactions give rise to hydrogen, because many of these reactions are metal high water reactions, which are naturally hydrogen producing. Okay, so this gave rise to some very interesting results. I'll show you, and this was converted into a reactor. So this is the reactor. So some of you who are in mechatronics and so on would find this work very interesting. Parth Mehta, who graduated from our group, he's the one who built it. So it turns out that it is primarily control systems based design that was actually used. We had to care for the fact that hydrogen should not leak. If there is any leakage, then there should be an alert mechanism, and there should be pressure regulation. There should not be any bursting effect of hydrogen. That means suddenly hydrogen should not be produced in large volume. These things were taken into account, and this was designed. Parth was extremely competent as a control systems person, and he actually helped in the development of this. And it is also a very safe unit. In fact, this unit used to work in my office, not even in the laboratory. It used to actually work in my office, and we filed a patent on the same. So I'll just show you the result. Okay. So primarily the logic is you start with dirty water which has mercury contamination, or okay, and then you try to get her mercury, and the alloy that is actually produced, let me see if I can. So he has used, all kinds of kitchen waste and so on in order to gather this. Okay, very interesting. And you can see this mercury, this pressure buildup. This is the hydrogen reactor inside which this mercury gathering is happening, and the alloy is actually used for production of hydrogen. It turns out that you can simply use a compound called sodium borohydride. If there are chemical engineers here, it's you have many open problems to work on. I'll be very happy to discuss problems here. For example, the recyclability of the final products that we are getting is a question that we don't have an answer to, and that can be very, very interesting. Okay, this is a project that got a lot of interest. So it's very easy to do. It's primarily a Arduino based system that he actually built, and it also has very high purity. So we measured the purity levels. It ends up being 99.9% pure, which means you can feed it into fuel cells and so on as well. Okay. Now the next question is, okay, now that we have learned the art of working with dirty water, harvesting sunlight for improving dirty water, even learned the art of making something useful from dirty water, let's say hydrogen. Can we do better than that, especially when it comes to solar based treatment of water? And in this context, we started working on aluminum indium nanoparticles. Okay. And the reason why we started looking at these nanoparticles was because aluminum standalone corrodes very easily, leaches out very easily, but aluminum with indium, there is evidence that it doesn't leach out very easily. And the question was, can we use it like antennas? Okay, antennas for sunlight. That was the question that we asked. Okay, it's a very interesting question. Think about it. Okay, just like in the case of RF antennas, you can use antennas, you can use structures, suitably designed in order to harvest radio frequency. Is it possible for us to make small enough structures to harvest sunlight? Because sunlight, the characteristic wavelengths are much smaller, right, when compared to radio frequency. That's the question. And so we started thinking about possibilities. For example, if there are nanostructures, if we can decorate nanostructures into dimers, trimers, tetramers, etc., is it possible for us to harvest it? When we began the study, we had no idea how to decorate it. Okay, so it was a curiosity-driven problem. It was something that we started working on because we thought there was potential to this idea of using nanoparticles as essentially antennas. And of course, we are not the first to actually think about it, because people in solar energy harvesting have actually been thinking about things like this, okay, for a bit longer. And we were able to design these nanoparticles so that they absorb very, very well in the visible region. And remember, most of the solar energy is in the visible region. So if we can absorb very well in the visible region, and these nanoparticles are absorbing very well in the visible region, we can harvest them, we can use it for solar energy harvesting, maybe we can use it for water treatment also. In fact, maybe we can also use it for improving amorphous silicon, because amorphous silicon is what is actually used in most of India. So last time I came to Kerala, I actually came through Cochin Airport, Cochin International Airport. Many of you who are Kerala based, you already know that there's a large solar farm that is attached to the Kochi Airport. And the idea was to make Kochi Airport as self-sustaining as possible. Okay. Now, all those photovoltaic panels are made up of amorphous silicon. And the question that I asked myself, and this was facilitated by Arvind, who took this work very seriously and did a fantastic job at it. The question that we asked was, is it possible for us to arrange these plasmonic nanoparticles on solar cells and use it to improve the harvesting efficiency of sunlight in a solar cell? And even if it is a marginal improvement in the solar energy harvesting efficiency, that can be fantastic, because on scale, because amorphous silicon is everywhere, even if there is a 1% improvement, on scale, that is a tremendous improvement in the amount of energy that we are actually producing through solar panels. And that's what we tried. So we started decorating these nanoparticles on amorphous silicon solar cells and started asking ourselves, how do these perform? Okay. And it turns out that, long story short, you actually get performance efficiency improvement. Okay. So I won't go into the mathematical details and so on here, but those of you who are interested in modeling, computation, electromagnetics modeling will find this work very interesting, and our paper is available for you to read. And I'll be happy to interact with you. Okay. Anyone, so those of you who even teach electromagnetics, will like this kind of work. We were able to show that overall, the efficiency improvement is about 1%, a little over 1%, when you actually use aluminum metal alloys, nanoparticles decorated on these amorphous silicon solar cells. Subsequently, what we did was we started putting these nanoparticles in basins for water treatment. So this is a basin of water treatment, and this is called as a nanofluid because it has nanoparticles inside. And what happens is, these particles that I have incorporated have some absorption efficiency variation with respect to wavelength. A lot of absorption is in this particular window, and it has to do with the fact that these particles oxidize when they are exposed to water and air and so on. Long story short, what happens is, the particle size of these nanoparticles plays a very important role, because beyond a certain size, you are scattering all the light. Below a certain size, you are not scattering at all. You would like to actually have enough scattering so that when sunlight comes in, it keeps bouncing back and forth, so that you basically have an infrared bath associated with water, so that you can harvest that energy. And remember, an infrared bath associated with water is same as water heating. And it turns out that by using these small nanoparticles, Sai Teja demonstrated that there was increase of temperature by 11 degrees. This was computational, but let me quickly take you to the experimental result. Okay, so what happened is that with nanoparticles, so all of this is the modeling. So those of you who like modeling, some of you might be chemical engineers, you might appreciate this kind of modeling, okay, which is primarily energy balance equations. Now, these nanoparticles that were made, we did the assessment of it using something called X-ray diffractograms. Subsequently, these were dispersed in water in small weight fractions. You can see the weight fraction is maximally 0.025 weight per weight. Okay. So what happens is your temperature, maximum temperature or saturated temperature that you reach is shoots up significantly. That means to say that by using these nanoparticles, it is possible for us to improve the harvesting of light and improve solar water heating. And in fact, you can get 14 to 16% enhancement using our plasmonic nanoparticles. Okay, plasmonic simply means shiny. Okay, for the non-scientists or for people who have not studied solid state physics or chemistry or something like that, it simply means shiny. So for example, gold jewelry is shiny because it's plasmonic. Okay, and another way of thinking about it, for those of you who are electronics engineers, electrical engineers, chemical engineers, and so on, is when light impinges on the surface of the metal, what happens is the metal is full of electrons, and those electrons go back and forth in collective oscillations. And those collective oscillations gives rise to good scattering. So in the case of gold, the very good scattering is actually seen, very good scattering is seen in the yellow region, which is why gold looks the way it does. Okay, that is why it is an ornamental metal, and so on. Okay. Now, these nanoparticles that we make are actually quite stable. They last a really long time in water. And of course, it turns out that if you disperse more than a certain amount of these nanoparticles in water, they settle down. So there is a tender balance. So like all problems in engineering, see, sometimes the science is simple, the engineering is hard. So this was very, very hard. It was a lot of work because we had to optimize and come up with the right surface chemistry, the right sizes, the right concentration, and so on and so on. Okay. So, and of course, the story began computationally. The story began with prediction of these particles as essentially nano antennas, you might say. Okay. And what happens in the case of water, temperature with respect to time of the day is that it increases and decreases for obvious reason. This is noon time. All right. So around noon, you have maximum temperature rise, and on either side, you do not have much temperature rise. All right, so that is what we have actually mentioned, and all these results can be by and large explained by using the scattering behavior of these nanoparticles. All right, so it is primarily the scattering behavior of these nanoparticles, and when you have these nanoparticles with the right composition, stabilized in the right manner, having the right shape, right size, right weight percentage, then we can get the benefit of scattering. We can get the benefit of creating an infrared bath associated with water that is there in the solar water still. So this is the solar water still. Okay, this is solar water still. So the design of it is also patented, because what we have done in this particular idea is we have actually used sunlight, we have used plasmonics, we have taken distillate, and now in recent times we have demonstrated that you can use this distillate in order to make hydrogen. Okay, by using water splitting, and that hydrogen is solar driven hydrogen. So there is some detail here. I will skip over this, but this is there in our rooftop. Those of you who come to our campus, I'll be very happy to give you a lab tour and show you this in our rooftop. So we have installed this in our rooftop. So this purifies water. This we have been using it recent times for experiments wherein water from our wash basins, etc., are collected and purified in our rooftop. Okay, so this is actually happening. Remember, the story started computationally, wherein we had this idea of nano antennas, and now this is happening. If you look carefully, here is a boy. He's the one who is carrying this work forward. So he's Adityan. Adityan is the one who set this whole thing up, who did the actual design, and he's from a mechanical engineering background. So it came in very handy, and he continues to contribute. to this particular area. Okay. Now, subsequent to that, it turns out that after the distillate was obtained, so this was the solar still, we collected the distillates. Once the distillate was connected, we wanted to generate hydrogen out of it. And to generate hydrogen out of it, the idea is if I have a semiconductor, and if I can use it for light harvesting, and if I can use it to separate electrons and holes, electrons can actually reduce water, holes can oxidize water, oxidation of water is oxygen, reduction of water will give rise to hydrogen. So until we came into the scene, this particular material, barium tantalum oxynitride, was used only for oxygen evolution. It was not used for hydrogen production. There was a PhD student who graduated with me, Bhushankar. One of his great contributions was the the concept of nano sizing in the context of ceramics. So copper oxide is a ceramic, and he in a single pot was able to show that you can have all of them essentially the same size with an accuracy, with a precision of plus or minus 1 nanometer. Okay, just to put it in context, your hair, if it's a healthy hair, the average thickness of the hair of a healthy hair is 150 to 170 micrometers. So you divide your hair along the width by 1,000 times, that is 175 nanometers. Divided further by 100 times, that is 1 nanometer. That is the kind of resolution that Bhushankar showed coming off our campus in the year 2017. So his papers are actually available for all of you to read and enjoy and sort of identify as opportunities. So, and of course, subsequent to that, we did a lot of modeling of why this happens, because it was actually a phenomenon we stumbled upon. It was an accidental discovery, but I wanted to actually come up with an explanation for it. So we came up with a thermodynamic explanation for it. And that also is published. But we utilize that to make copper oxide self-similar particles, particles that are essentially all the same, and connected it to barium tantalum oxynitride. This one is a p-type material, this is an n-type material. So it is like making a p-n junction, the way in which many of you electronics engineers teach your students or have made yourself in your device physics experiments or device physics courses. Okay, wherein you have n material, p material. If they sit together, you have a junction that forms, and that junction will have a depletion region, and that depletion region is actually very nice for separating out electrons and holes. So we made this, and we were able to show that it actually has a combination of barium tantalum oxide and oxynitride along with copper oxide, and we studied it microscopically and all that. So given the composition of this particular audience, I'm going to basically go to the result directly. Okay, so here we are using this semiconductor and in a biased setting. That means we have actually applied a negative bias on this particular material and a positive bias on a counter electrode, and we were able to actually get hydrogen production. And it turns out that this hydrogen production compares with commercial distillate. Remember, we used plasmonics, sunlight to get this distillate. Commercial distillates performance is comparable. And we want to do better than this, and it might be possible to do better than this by working with other materials that are also long lasting in water, which might be better for water light harvesting and so on. So that work is on. Okay. So right now, the best current density we get is 1.4 milliampere per centimeter square. Our eventual goal is to hit 150 meters milliampere per centimeter square, so that this can basically become technologically viable. It is possible because these particles are pretty big. Though this particle is very small, this particle is very big. So it is a huge chunk with small chunks. So now we are pursuing efforts to nanosize it. And remember, if you can reduce the radius by 10 times, your area will actually multiply by 100 times, because area goes as r square. Okay. So we want to try those experiments so that we can improve this current density and we can improve the hydrogen throughput. What is the big take home for all of you? Clean water, energy, and hydrogen, they are all linked. Today, by virtue of this kind of work that is going on, the next generation hydrogen, the next generation energy, the next generation renewable energy harvesting, the next generation clean energy production, clean water production, they are all connected. Now, in this context, something that stimulated my thought was, what about energy storage? Because energy harvesting, water treatment, hydrogen, all of them are connected. But what about energy storage? Because that becomes very important in the renewable energy transition. Why? Because of the following reason. First of all, we should appreciate that renewable energy transition is important. The reason being that even today, we primarily depend upon coal. Even today. Okay. And please notice that we are, though we keep talking about sustainable development goals, in terms of global energy consumption, we are still at the peak of oil consumption, gas consumption. Coal peak was a little behind. But right now we are in the oil peak, gas peak. Okay. And gas peak will actually be in times to come. Right now we are in the oil peak. All right. So the energy scenario in India is extremely challenging because we need an additional 2.6 lakh crores to be invested in clean energy segment. Out of it, only a very small fraction has come in so far in the last 5 years. What we want is a cumulative of this. Where we are is 1/4 this. Ideally, we should actually have much more than this, which means to say that the R&D support is also not as high as it is. So this is a time wherein we can actually generate the know-how, maybe through computation, maybe through AI, by using analytics, etc. So that as and when the money comes 3 years from today, 4 years from today, because that is sort of what we anticipate, there's already money, but it will get better for R&D because it's an inevitable trajectory. We require to actually move away from this. We are required to move away from oil peak, and oil peak is a global reality today. It is the reality in India also. Okay, so energy storage, if we can make it very cheap, we will boost investor confidence, and the amount of money that is pouring into renewable energy will increase. This is why I thought it would be necessary for us to invest our R&D strengths in renewable energy storage also. Now, it turns out that renewable energy is full of fluctuations, which means to say that you need to have energy storage. Okay. For example, sunlight is there during daytime. It doesn't exist at night. So it's full of fluctuations. Intermittency is associated with renewable energy, which means to say all these energy storage technologies need to be there. Now, as a researcher, of course, I was looking at areas wherein we can contribute maximally. All right. So it turns out that all of this hydro, wind, solar, we are on the upswing today. You can all visit the Energy Storage Association's website. You will find some very nice data associated with various countries and so on as well. In all of this storage, system efficiency is important. So those of you who are electrical engineers, power systems engineers, etc., have a lot of work to do. Those of you who are chemical engineers have a lot of work to do. Transportation of energy storage. Demand response. Demand response can definitely be a lot of AI research, can be a lot of data science research, can be a lot of forecasting based research. Those of you who are in power engineering could actually think about power forecasting. Okay. Now, the bottom line is that alternate energy storage is required because renewable energy storage is required, and that is required because clean energy storage is required. But this has to be done with minimum energy loss, low cost, eco-friendly manner, and in a manner such that it is reliable. The current approach is relying on batteries primarily, although fuel cells, there has been waxing and waning of interest, supercapacitors, electrolytic capacitors. These are very materials heavy domains, and I thought that contributing here would be very reasonable for the following reason. Number one, the first reason, if you look at the status of energy storage technologies, you will find that batteries are somewhat mature. Sodium ion batteries still not mature, okay? But lithium ion batteries are everywhere. Flow batteries have gotten to the point wherein industries are happy to take it up. That doesn't mean that all the chemical engineering research is exhaustive. It doesn't even mean all the electrical engineering research is exhaustive. Okay? But you will see that it's very close to adoption, which means to say for government project calls wherein they want industry partners, etc., this is actually a good area to enter. I was interested in something a little bit more fundamental, so that in 10 years timeline, there would be a substantial footprint. Okay, that is why we started working on supercapacitors something like 5 years ago, and now I've started seeing the impact of it in the real world. Okay, so it was actually a good move to start supercapacitors. So this is something very important. Those of us who are doing research, we should wear multiple hats. First question we should ask ourselves is, what is it that I'm interested in? What is it that I can do? What is it that I can do with the resources that is available? The second question is, what is it that I should do that is very relevant and important? And thirdly, what is it that I can do from an academic standpoint that will have a 10-year impact ideally, because the shorter terms can be taken up by industries and so on. Long-term impact we should be able to envisage. Okay, we should be able to take that up. So supercapacitors, they are very attractive because if you look at supercapacitors, and these are the middle three columns are supercapacitors, you will find that they can operate in a very wide temperature window. Okay, and the most important thing is look at their charge discharge cycles. The minimum you get is something like 1,000. These are just nominal number and these are in thousands. Okay, so you will find that you can, if you compare that with batteries you can push it to a few hundred, maybe now to a few thousand with great difficulty. But but supercapacitors, compare its cyclic stability with the cyclic stability of batteries. You'll find that the cyclic stability of supercapacitor is much higher than that of batteries. But notice its power. Its power is much higher than batteries as well. Battery is 0.3 to 1.5 kilowatt per kilogram. This is 2 to 10 kilowatt per kilogram. But specific energy is very low, and so we decided to work on specific energy. Okay, so what are these supercapacitors? They are like the capacitors you teach in your electrical engineering undergraduate laboratories. Okay, the big difference is that these can actually have several farad capacitance. For example, this is a commercial supercapacitor that is rated at 2.7 volts, but 150 farad. The kind of capacitors that you use in your electrical engineering laboratories and so on, they are just a few picofarads or microfarads. Now, it turns out that the configuration of it is very simple. You have an electrolyte that is between two different electrodes. So it's an electrolyte. You have a separator. And then you have some material that is sitting on the electrode here and here so that you maximize the area. And what is the logic? The logic is when you're applying a potential. So let us say that this is one of the electrodes. This is what you have painted on top of the electrode collector. And this is the ions that are freely floating. When you apply a potential, many of these ions will come and actually stick to the surface, and as a consequence, a tremendous amount of charge can be stored. So charge discharge can be quick when compared to batteries. Okay, and power densities are high when compared to batteries. Power density is conservatively 10 times higher. It can be as much as 100 times higher. Why is it very attractive? If you combine this with batteries, then wherever there are fluctuations, you can offload it on supercapacitors. And because supercapacitors have such a long cycle life, and because you have offloaded the batteries have not experienced any sudden fluctuating load currents, and as a consequence, the batteries last longer. If you can make batteries last longer, then you have reduced the footprint associated with battery. You have improved the life cycle associated with the battery. Now, there are different kinds of supercapacitors. We will discuss some metal oxide and oxynitride based supercapacitors and activated carbon based supercapacitors. This activated carbon, we started working with kitchen waste and agro waste and so on for supercapacitor production, because converting waste to energy storage devices and using that to store solar energy would be wonderful, because then we would have converted waste to wealth. And this waste can come from farms, it can come from kitchens. If it come from farms, it gives additional income to farmers. It again connects to decent living, improved income, improved quality of life, and SDG. And we look at metals also. Now, so the approach that we took is we start with computation, do the experimental validation, and finally build the device. Okay, and the genesis of this is the work of Dr. Kaushika. Okay, and in fact, she was instrumental in developing the capacity for us to understand how defects work in materials and how these defects in materials can be used for storing charges or for transport of ions and so on. Okay, I won't get into the details of it, but long story short, it is possible for us to actually ask questions like, if I heat this material, what would happen? Cool this material, what would happen? What would happen to the ions? What would happen to the composition and so on? This is the kind of work very few people in the world are doing today. It's time consuming and difficult, but I wonder if AI can actually help, because when we started this work in 2018, many of the tools that are available today were not available then. So we painstakingly derived the interatomic potential and so on. But now, by using multi-feature regression models and so on, it is possible for us to do this. So we should certainly consider doing it. those of you who like to do statistical modeling and so on, and who would like to apply it to a problem like this, please talk to me. I would be very happy to at least foster the thought. Now, around the time we cultivated this capacity, it turns out that I learned that India was actually one of the best suppliers of cerium to the world. Okay, so if you look at the metric tonnage production, it turns out that, see, there are not very many things that we export, but we do export ceria. And we export ceria without a value addition. And we export ceria to China, which already has a tremendous reserve of ceria. Now, it turns out in the last few years, we have actually discovered fresh sites for ceria mining. Okay, and so people in industry started asking me, is it possible for us to add value? Because what was happening was we were exporting it to China. China was value adding and selling it to us for 10 times the price, 15 times the price, which also means to say that that industry was not forming here in India. And as a consequence, we decided to ask the question, is it possible for us to use this material to store energy? Okay, so it turns out that ceria in literature, many different kinds of compositions have been tried. Okay, many different compositions have been tried. People have tried ceria doped with nickel, cobalt, manganese, and so on. A variety of stoichiometric compositions have been studied, and its abundance in India, at least, is not a problem. There is a fair amount of literature, but not much on use of ceria for energy storage. Okay, so we decided to apply this know-how to energy storage. And the reason why it is useful for energy storage is because cerium 3 plus can become cerium 4 plus, cerium 4 plus can become cerium 3 plus. That means you can charge and discharge ceria. Okay, so thanks to Dr. Kaushika's work, Dr. Saurav Ghosh, who is now in the electronics department of Savita, he adapted Mott Littleton method. That is the method that we developed, adapted, okay, to study the defects in ceria. Okay, and we demonstrated that if you have chromium that is doped into ceria, it will basically make the production of oxygen vacancies. That means oxygen will fly out of the material more easily. Now, if oxygen flies out of the material more easily, then this whole cerium 3 plus to 4 plus business can become easy. Okay, because you're producing a lot of mixture of cerium 3 plus and 4 plus. So this is a slightly materials heavy slide, but what we demonstrated is that if you put chromium in ceria, indeed you get more oxygen vacancies. That means you can store more charges in it. And what did we find? We found that we were able to store 3 times more charges. It was giving 328 farad per gram when compared to pristine ceria, which we export to China at 103 farad per gram. So this was reported from our group, in fact, 4 years ago. And then Dr. Saurav Ghosh also developed devices based on this. And these devices function with 100% capacity retention for 10,000 cycles. Okay. The big challenge, of course, is energy storage. Power, it gives fantastic power, energy storage, but we are now able to actually do this in our own country. We are able to actually make make high performance supercapacitors in our own country, and we have covered the full supply chain from predicting to realizing it experimentally to making the devices to testing it and getting it to a point wherein it will be attractive from an industrial standpoint. So this is one example of how powerful computation is if it is done with the right perspective. Of course, you need to know the science also. In the absence of the science, it's not, computation alone will not help. So some depth is sort of required. Okay, so this is another case study wherein we looked at zirconium that is added to ceria. Okay, and when zirconium is added to ceria, it turns out that you're able to again store a fair amount of charges in this particular system. So the key thing is, so this is current and this voltage. So it is just like your Ohm's law curve. The big difference is you can see that it is not at all linear, this material, when it is put in a device, because what happens is that you have some energy that is stored. This hysteresis between in the IV curve, between the charging and the discharging, tells you that some energy is actually stored in the curve. And also these peaks basically demonstrate the C3 plus to C4 plus or C4 plus to C3 plus conversion. So these peaks stand for C3 plus to C4 plus. This stands for C4 plus to C3 plus. Okay. So it is possible for us to read into these IV curves, very similar to what electrical engineers do in their Ohm's law experiments, but read more into it. And these are electrochemical experiments. Read into it so that we are able to develop next generation energy storage devices. Now, it turns out that we have our own model to study this now. So we have developed it. So maybe I can just explain the science behind the thought that was there behind developing this model. So if you, it turns out that you can use redox additives. That means, see, the Syria that you're using already has C3 plus to C4 plus dance going on. Okay. If the electrolyte also has such dances going on, you can store a lot of charge, it turns out. But it was not possible for us to characterize the exact contribution of this electrolyte, and which is where Dr. Saurav Ghosh, during his PhD, he ended up developing this model, and I have simplified the model in this particular slide. So basically, the idea is to check how much redox electrolyte is sticking to the surface. It's usually just a few micrometers thick, and then use that information to delineate the contribution from the redox electrolyte. So for which we did, we were able to actually test this, and it is in agreement with other slightly more complex models. So this model can actually be used whenever you are working with redox electrolytes. So um, the stability of this is fairly good. The zirconium dope, actually the redox electrolyte based one, but the stability is not the best. So redox electrolytes will help you improve the energy storage. Stability is a problem. So here is an AI problem where some of you who want to do data science on problems like this, here is an AI problem or a machine learning problem. Can we identify moieties in the electrolytes that can predict very long cyclic stability? Okay, this is something that would be very useful from the point of view of optimizing these devices. Okay, so we can think the details of this problem in person or over phone, etc. If you are interested in discussing ideas and all that. So we have been able to, as a consequence, previously improve energy storage by a factor of 3, an additional factor of 16 through proper redox electrolyte usage. The problem is the latter increase is dramatic, but it is not cyclically stable. The former improvement, which is improving by adding dopants, is cyclically stable, but it's not as dramatic. It's still dramatic because it's still a 3 times improvement. And it still makes it very attractive for indigenous development of supercapacitors. So what is next? What we have done so far is we have explored specific capacitance improvement by using doping. We have selected a suitable dopant. We know how to make, how to model these dopants in these materials. Model predictions actually helped us optimize the dopant. Then we were able to predict the redox. We were able to use redox additives. We developed a model for redox additives contribution, but we don't have a model for optimization of this. So that would be very interesting. Okay. So is it possible for us to predict the, another question to ask is, even before you make a material, is it possible for us to do performance prediction? And those of you who are from the world of circuit theory, systems engineering, and so on, for you, it is very straightforward. Materials, it was not straightforward because it's very complex. It's closer to the sciences. It has a lot of fuzzy parameters, lot of variables. But now in this story, I'll tell you that it's actually possible. We are getting there to that level of maturity, even in the world of materials. Okay, so it's possible for us to actually develop databases, make predictions, and do regression analysis for known compositions, extrapolate for new compositions, and then we can do experimental validation. So here is an example. So what do? You identify the material. So I looked at cerium oxide, for example, thought that there is value and potential for it in our country. Then it turns out that I knew that nitrogen incorporation is attractive. And then the question was, even before going through the painful process of making that material, because it's very difficult to make the material, can I predict whether it is worth it? Which is where data science became important. Okay. And but please remember, it's not always dependable, and all of you who know statistics know this. Okay. So it turns out that we made the database. So we developed grades for the various materials that are there in literature, and we graded them into these 4 categories. So you have D, which is the very high category, A, which is a category wherein you have 200 farad per gram or lesser, and it turns out that most of the materials reported are here. But please remember, this is more than sufficient. Right? It's very workable. Even this is sufficient. You might have champion values. For example, there is this class D materials, but then they may also be very difficult to make. Okay? So many of you are from computation, so I don't have to explain this in great detail perhaps. But long story short, it is possible for us to actually work with conceptually very complex data set by using models such as multi-layer perceptrons. And these perceptrons are basically neural networks. Okay. And what are neural networks? Neural networks are basically a set of layers that are all interconnected through nodes. So you have these nodes, you have input layer, hidden layer, output layer. It's a lot like your computer networks. And a lot like the way in which queuing theory is applied to computer network optimization, you can do the same thing with large data today. So we actually decided to apply those kind of algorithms to this kind of materials problem. Okay. And please remember, those algorithms actually come from the work of network engineers and so on. Okay. So it is sort of a adoption of those things that we actually use. Okay. And of course, for complex data, what you have to do is you have to actually do both forward propagation and backward propagation till the weights of these nodes are proper, so that the training set will sufficiently trains the nodes. That's the idea. Okay. Now, random forest, it's actually a method. It's a algorithm. It turns out, and it's actually a ensemble learning algorithm because of the fact that it basically divides data set into multiple subsets, and then it tries to actually come up with outcomes, and it tries to optimize the outcomes in a manner such that training is possible between these various trees. Okay, so it's a decision tree paradigm. So we use this decision tree paradigm, and it turns out that I'll jump straight to the final result. Random forest actually works very well, okay, for this kind of data which is very noisy. For those of you who work in device physics and so on, this should not be surprising. It is noisy data. It is very difficult for us to actually tell precisely what the performance would be precise, because there are so many parameters that go into it: the morphology, the growth parameters, the process parameters, this, that. There are comfortably, many dimensions associated with this data. Their random forest tends to do quite well. So we used random forest technique, and it actually worked quite well. Okay. And then we also, from the materials design point of view, decided to use principal component analysis. Sorry for this typo. Sorry, I did not notice this while making this slide. So the principal component analysis allows you to actually pick the key variables when you have a large number of variables. And we have done this in the context of light emitting devices, it turns out. And we have a early perspective article. In fact, our articles will be among the first from India. So you can check among the very few from Asia in the early days of materials informatics and so on. Now, of course, it's becoming very popular. Large number of people are in the game. But then you will find the work of Santosh Behra, who is now in NIT Andhra, and Smarak Rath, who will soon be finishing his doctorate. Their work to be among the earliest works coming from India. Okay, and this principal component analysis allows us to breathe a little bit more science into high dimensional data. Otherwise, it's very difficult to sort of wrap our head around the physics or chemistry of the problem. Okay, it's a little bit like this. Think about network traffic problem. Okay, network traffic associated with, let us say, Chennai, or whichever city you are in, or whichever town you are in. Then computer network traffic. It is associated with the social psychology of that place. For example, maybe evenings, a lot of people are actually watching YouTube videos or something like that. So while in the afternoon, most of the people are busy, so they don't watch videos. And then early in the morning, they are busy making food and whatnot. So again, there's not a lot of watching. So there is some psychological underpinning. But if you do not reduce the number of dimensions, okay, associated with traffic, it is impossible for you to connect it to the underlying science. That is why principal component analysis is critical in problems like this. Okay, and it helps us actually come up with predictions. So it turns out that random forest performs very well, and it turns out that multi-class classifier along with random forest also performs comparably. Okay, so this is good news, because these can actually be rendered in an efficient manner. Some of you are from computational engineering and so on. So for people like me who are users of these algorithms, if these algorithms can be made as computationally efficient as possible, it is useful. We can publish papers on that. We can actually develop new research. Okay, so so this should possibly give food for thought for those of you who are in those areas, such as algorithm, computational complexity determination. Those of you who study the complexity, computational complexity of algorithms, want to minimize the computational complexity of algorithms, maybe for a specific class of problem. Okay, those are things that we could actually discuss and take things forward and so on. The base learners that we are working with are trees, logistic regression, support vector machines, and so on. Okay, and these are things that I suspect many of you know very well. Okay, by now, perhaps because you're already 2 or 3 days into this workshop, but also many of you are from computational engineering and so on. If not, you are welcome to foster a discussion at the end of this lecture also. Now, there's something called confusion matrix, which is also very, very important because it helps us determine the precision with which we are making predictions. And it tells us how biased our algorithm is, our model is. Okay? And if our model could be very biased, for example, see, the simplest example for many of us who teach, for example, so I am a teacher, so the simplest example would be in a class that I'm teaching, a course that I'm teaching. There, on an average, I do not expect the number of students who fail to be more than the number of students who succeed, who pass, on an average. So year after year, the data that I'm giving is associated with that. So what will happen is that it will be biased towards success rather than the model might have a bias towards success than towards failure. So there could be a lot of false positives. There could be a lot of false positives. And so it is very important as a consequence to know false positives, false negatives, and so on. And this statistic can be obtained by you defining precision, recall, F1, and so on associated with confusion matrices. And it turns out that when you do this multiple model building, the random forest actually does quite well. The multi-class classifier along with random forest actually does the best. Okay, and random forest also is comparable. Okay, very comparable performance. So that's very interesting. Random forest is actually incredible for this kind of complex data, which is truly multi-parameter. Okay, so I'll at this point also go to attribute prioritization. So remember the example that I gave you associated with social psychology of a city versus the network traffic of the city. Okay, so likewise, in the case of problems like this, in order to breathe science, we have to identify what the biggest and most important attributes are. And these attributes can be actually determined by using feature importances and so on. And it turns out that these are the 4 most important attributes. And today, experimentally, these are the attributes that I optimize in optimizing our devices. So you can see that between machine learning, between materials informatics, and the kind of models that we are developing, and the experiments we are doing, there is a synergy. Okay, so so the cyclic stability using our model can be predicted between 90 to 100% with 90 to 100% confidence. Okay, so the big question to ask is whether it is less than 200 farad per gram or greater than, because 200 farad per gram is sort of the basic grade. Okay, and we predicted that for cerium oxynitride, with despite its very low specific surface energy area, we would actually get more than I mean a very, very high cyclic stability, almost 1 lakh. Okay, there is almost 95% performance retained over 1 lakh cycles. That was a prediction, and we were able to show that in experiments. So this is over 10,000 cycles. You can see that the performance is more or less the same. And in the paper, we have further evidence that even up to 1 lakh cycles, it is actually okay. So cyclic stability of 100% even after 10,000 cycles, and something like 94% after 1 lakh cycles. Very, very good performance of this particular material in terms of cyclic stability. Okay. So a lot of papers have actually come out that have cited this work, because at the time that we published this, this was the oxynitride that was a champion, okay, worldwide. So very interesting work has actually come out of this kind of informatics. As I said, we were among the early adopters, which helped us. But all of you could actually, in your own respective areas, get creative and ask these kind of questions. Okay. Now, subsequently, we turned to, again, for energy storage purposes, decided to turn to farm waste, kitchen waste, and so on, and make activated carbon out of it. Activated carbon is simply pyrolyzed kitchen waste, biomass essentially, which has a lot of active areas on which charges can be stored when they are in a supercapacitor configuration. So I am very sure that those of you who are electrical engineers and so on, you might not have connected semiconductors or your device physics to cucumbers and bitter gourds and so on, but it is possible. Not in the context of silicon, of course. It's impossible in the context of silicon, but it's possible in the context of supercapacitors. Okay, so this is an example of a snake gourd derived activated carbon. It's very holy. That means to say that it's very full of holes. Okay, please remember that this is the scale bar is 500 nanometers, so it's full of holes, full of holes. So it can store a lot of charges. So we were able to get grade A supercapacitors, 206 farad per gram at 1 ampere per gram. So tremendous amperage, 1 ampere. Those of you who are from electrical engineering know that 1 ampere is very high. Okay, so even at this 1 ampere per gram of the material, we are getting 206 farad per gram, starting with snake gourd. Okay, converting that into activated carbon and so on, which is why subsequently we were interested in solving the problem in North India, wherein the paddy burning was an issue, is an issue. So those of you who are from North India, you Delhi and all, you would know this, and also Punjab and so on. Paddy burning is a very, very big issue, paddy waste burning. And the air pollution associated with it is a severe concern for government, for agro scientists and so on, and certainly for the public health. So that is why we turn to this kind of research. I'll take you to maybe some recent work at this point. So it turns out that um, its voltage retention is fairly good. So it maintains 90% voltage even after 2 hours of charging. So you can charge it, and even after 2 hours, 90% of the voltage remains. That means 90 plus percentage of the energy is still available. So you can actually rapidly charge it and keep it for 2 hours. So now there is a startup company that is spun off, which is actually trying to use this kind of supercapacitor materials and supercapacitors for on-the-go electronics. Okay, so there is some work in that direction that is going on. This is Syria rendered in nanoflake form by Dr. Anith. So you might remember the Syria story. We have extended that story along with the activated carbon story, and we are also rendering it in low-dimensional forms. I will quickly jump to the conclusion maybe at this point, because we are very close to 7:30. I wanted to show you some of this because some of you who like to build things and all will find it very exciting. So for these capacitors, because these capacitors, the testing is very hard. Okay, the testing associated with them is very hard. We had to make because they have many 100 farad capacitance possible. So we had to actually come up with our own test bed. So this test bed is different from the multimeter that can actually measure a few picofarads, millifarads, and so on. This test bed allows us to actually charge a several hundred farad supercapacitor and measure how much energy is in it. So mechatronically, we are actually evaluating this, and this test bed has also helped us test, new modules wherein batteries and supercapacitors are connected. Wherever fluctuations are there, they are offloaded onto the supercapacitors. Wherever fluctuations are not there, they are offloaded onto the batteries. Okay, so there's a company on this now. So the big take homes are fresh synergies are possible between theory. See, today we went through basic science, okay, and computation and informatics and experiment. It is possible to synergize. And very often materials is a convergence space. Those of you who are interested in Industry 4.0, it is possible for you to actually usher it in a fresh manner in our country if you can also start thinking about materials innovations as it pertains to your own area, whether it is chemical engineering or electronics engineering, electrical engineering, whatever it is. But it is possible. It's an opportune time. Many thanks to many people involved, many of whom who graduated from our group already. Dr. Sudha Priyanka, Dr. Bhuvaneshwari, Bhuvanasundari, Dr. Santosh Behra, who is currently in NIT Andhra, Dr. Kaushika, who is now in Indian Institute of Science. She was the one who developed the thermochemical model. Dr. Saurav, who is in electronics department, Savita. Dr. Anit, who is with us, who works on nanomaterials for energy storage and conversion. I forgot to mention the name of Sandeep here. Sorry for that. So this is Sandeep. Sandeep is the one who does the spin-off, who is taking, and then many people who continue to work on plasmonics. Arvind Pujari, Abhimanyu, Sai Teja, Ambesh has already migrated to a company, and Adityan, who is with us, who is the person who is doing this plasmonics for next generation water treatment and so on. Special thanks to many colleagues and collaborators. I have been very collaborative all my career, all through my education, all through my career. And so many thanks to many colleagues, professors from across the campus, across the country, across the world, and many funding agencies who and occasionally industry participants who made all of this possible. Watch out for fresh patents and publications that will come from the group in new agro sensors, industrial sensors, novel recycling approaches. So we are taking up many pertinent problems on those fronts. In many of those fronts, all of your minds can be put to very productive use. So watch. In addition to things that I have already discussed, you are welcome to watch out for all these publications from the group. They are all the publications that are already out are available on Google Scholar. If you have any difficulty accessing any of those, please let us know. This is my WhatsApp number, and this is our group. I maintain a fairly updated page where you will get to see activities of the group and even social outreach and interdisciplinary collaborations, intercollegial collaborations, and so on and so on. Thank you, and I'm open to discussions, questions, queries, and so on. And I hope many of you have populated the chat box with your questions, spontaneous questions. So, let's see. I'll stop here. So Dr. Della and Dr. Ravi, over to you.
So I think participants, if anybody wants to interact, you can interact. Yeah.
So they can also post messages. I do not, as I said, I'm having some trouble.
Sir, one question is there in the chat box. Sir, how efficient is this supercapacitor for the design of general purpose computers?
Yeah, that's a very good question. That's the kind of question that deserves a further study. But I can tell you the following. There is, even in the case of supercapacitors, what happens is you have, in the case of laptops, there's a lot of intermittency because your CPU demands basically fluctuate a great deal with respect to time. So whenever those sudden fluctuations come, if you can offload onto supercapacitors and then increase the life of your batteries in your laptops, that can be fantastic. Very often, those are actually the limiting factors associated with how long a laptop is used. In addition to, of course, the life of the IC chips and so on. But those fluctuations can be handled better if supercapacitors are used. Now, how can we actually improve the gravimetric energy density of supercapacitors so that it is very attractive for general purpose computing is a question that is worth exploring, and I'll be happy to sort of look into the details there with you, whoever it is. I don't know who asked this. Yeah, okay. All right. Questions? Okay, so somebody asked a question on CTAB. Yes, Dr. Malarviri. See, I'm not able to somehow see all the messages. I don't know why. So, if, Dr. Ravi, if you could help me, that will be very helpful. I'll stop sharing. Maybe that will help also.
Sure, sir. I will read out.
Okay. You can mention the name of the person so that I can address it to them. And
Okay.
please read out the questions. Yeah. And how many questions are there? May I know?
Approximately 3 to 4, sir. 3, I think. Two
Okay.
more there.
Then it's all right.
Like
Okay. I can.
CTAB.
Okay. So Dr. Malarviri says CTAB good for SE performance. See, CTAB is very attractive if you want to actually achieve things like digestive ripening, one of the things that I actually mentioned previously. Now, I think, Dr. Mallavadi, you are asking a question on, can we functionalize the surface of these materials and improve the performance? Typically, CTAB would actually reduce the number of active sites because it's a surfactant. Okay, so but if you want to think of it, think of using surfactants to process the material. For example, you want to nanosize it, but at the same time have some kind of size focusing and all that. CTAB is quite good. Once again, I would refer you to Bhushankar Taluri's papers when he was a PhD student with us. Bhushankar, Bhusankar, Bhushankar Talluri, Talluri, Bhushankar, Dr. Bhushankar Talluri. So he, and prior to him, Nia Mary, Niya, Nia Mary, Mary, Mary. These people worked on these areas where surfactants were used to tune the properties of materials. And then you have to ask more specific questions. For example, CTAB standalone will not help because it will actually passivate the surface. But can CTAB be used as a vehicle to achieve certain morphology which will improve specific capacitance? That's a good question to ask. That's a question that can actually be pursued from a research standpoint. Okay, so I hope that helps you, Dr. Mallarvedi. You may unmute and speak and engage if you are interested. I'm very happy to engage, and as you can see, I have no hesitation in sharing my number and all that. So feel free to reach out, ask questions and all that. Dr. P. Bhagat said, though not from material science, I could know the applications of ML models. Very good. So Dr. Bhagat, which background is, what do you do as in your research? Okay. All right. So that's it, I suspect. So we'll, is there any other question, comment,
No, sir.
suggestion? Okay. So we will close the discussion. All of you are welcome to sort of write to me. So Tiju Thomas at SMail, let me just type it out. Tiju Thomas at smail.iatm.ac.in. So as you can see, I mean, for research, I'm always happy to be available. So please feel free to ping me, and especially for research discussions that are abiding and persistent, I'm happy to be available. Okay? And serious. What is that? Okay, Dr. Bhagat, you could unmute and speak now. It seems like you want to speak some. Okay, he could not unmute his mic, he says. So maybe you can allow him to. Okay, he's from speech processing. See, the closest I have come to using is image processing in materials. Okay, so those of you who are into processing might actually be, in general, signal processing, let us say, could explore materials problems. There are a lot of problems there. So, and of course, now with AI based things, one could ask very, very creative questions like, can Gen AI, for example, be used in on top of the kind of feature modeling we have already developed in order to actually come up with even more accelerated predictions? That's a good question to ask. So, okay, thank you very much. All right.
So we thank you for your engaging and interesting talk. I think all participants are also happy, but I think nobody could interact maybe because of net issues. Yeah. Thank you very much, sir.
Thank you. Thank you, Dr.
Once
Della.
again, thank you, sir.
Thank you so much. Thank you for having me over. Thank you. Yeah. See you both.
Yes,
Bye.
sir. Bye-bye. Thank you.
Bye.
Thank you, sir.
Sir, I think